Hello, myself Shomrat Paul. Presently, I am working as an assistant professor in the Department of Electrical and Electronics Engineering at Swami Vivekananda Institute of Science and Technology. In my first lecture session, I am going to demonstrate the topic on Thyristor in detail, its working principle, its construction, its VI characteristics, and so on. Before going into my lecture session 1, we should know what is the basic difference between uncontrolled switch and controlled switch. In case of uncontrolled switch, the good example is diode. And as we know, the normal characteristics of an ideal diode, it will provide the low impedance state for forward biasing condition, and it will provide the high impedance state for reverse biasing condition. As well as the diode starts conducting from 0 degree to 180 degree and it stops conducting from 180 degree to 360 degree for a complete cycle. As well as we cannot control the conduction angle between 0 degree to 180 degree. That is why this is called uncontrolled switch. So if the diode is implemented for any designing purpose of the converter, then the output voltage and current from the converter circuit cannot be regulated and controlled also, which can be overcome by using some control switches. For an example, that is Thyristor, GTO, transistor, IGBT, MOSFETs, and so on. By using those kind of switches, its behavior just like a diode. Again, it will provide the low impedance state for forward biasing condition, and it provides the high impedance state for negative biasing condition. But unlike a diode, it can conduct, means we can control the conduction angle between 0 degree to 180 degree anywhere. That is why the output voltage and current should be regulated and rather controlled. That is why control switch based converter circuits are very useful for industry application through which we can control or we can achieve the controlled or regulated output power. That should be very much useful for the drive application, locomotive, and any other applications. So, Thyristor is a good example for the control switch. So, today our topic is Thyristor. What is Thyristor? Why the name stands for Thyristor? As the Thyristor is a solid state device, or we can say is a semiconductor switch, and which is behaving like a transistor, and its characteristics is almost similar to a Thyraton tube. That is why the name stands for Thyristor. On the other hand, we can say Thyristor is working as a rectifier, and that to be controlled, and silicon is normally used as a dopant during manufacturing. That is why Thyristor is called silicon controlled rectifier, or in short form, that is SCR. First, construction. So let me draw the diagram first. It has 4 layers like this. That is P, that is N, again P, and last one is N. As well as it has 3 terminals. This is anode, this is cathode, and this is gate. It's a very important terminal, gate terminal, through which we can control the output voltage by applying the appropriate gate pulse through some gating circuits. And it has 3 junctions also. We can name them, that is J1, J2, and J3. So in this particular case, one thing that is keep in your mind, so what will be the circuitry representation or symbol? Though the symbol is just looking like this, just depending on the 3 terminals, that is A for anode, that is K stands for cathode, and that is gate. So this is the circuitry representation or the symbol of the switch we can draw this kind of symbol during any operation. And to be more detailed, the circuit, the diagram, the basic construction can be redrawn like this is as a huge space occupied, that is anode, and is the anode terminal that is actually manufactured by aluminum, and the other layers, that is 3 layers, P, N, and the last one is here the gate is applicable and here the other thing is there, that means cathode. So this is actually the cathode terminal and this is actually the gate terminal. That means we can understand this cathode and gate which is located nearby. As well as the 3 layers we can identify it easily, that is P, that is N, that is P, and this is N, last one. And the 3 junctions just similar in the similar way, that is J1, that is J2, and this is J3. And the total mechanism that can be tightening by an additional nut, that is called actually threaded stud, just that is mounted over the anode, this is called actually threaded stud. Which is normally used to tightening the total construction or the structure, as well as for application purpose somehow it can work as a heat sink. Okay, so this is actually the total construction of the thyristor. In this particular type of construction, see it very carefully. This lower part of which is located, this is lower part which is directly connected to the cathode terminal and which is located and close to gate terminal, this will be highly doped. Means the electron density is higher with respect to the other layers. And the upper surface, that is actually which is called anode terminal, that will occupy the huge space to provide the low resistance path. And this is the threaded stud I told you before. It is normally used to tightening the total structure and for heat sink for higher application. As well as it should be keep it in your mind, this kind of structure, it has a particular ratings for application purpose. If the ratings is very high, normally the thyristor can handle near about 30 megawatt power, that is 30 megawatt power it can be handled. Okay, that means the current handling capacity near about, that is 10 kilovolt, and current handling capacity that is near about 3000 ampere is a very big in magnitude. Sorry, it is 3000 ampere. So that is actually the specification of the thyristor normally used for application purpose. Now working principle. Listen it very carefully. Okay. Here we cannot say the anode is positive, cathode is negative. Here we can say the anode is more positive with respect to cathode, like this. So suppose consider the anode is more positive with respect to cathode. That means then we can say the device is under forward biasing condition as the current starts flowing from anode to cathode. See, in this particular case, what happened? Now think about a junction J1, okay, and current try to enter anode to cathode in this direction. That means this PN junction, which is defined by J1, that is in forward biasing condition, as well as the junction J3, which is connected across the lower PN region, that is also in forward biasing condition. That means there is a no question for depletion layer. Whereas the junction J2, which is connected across NP region, that means this junction can be worked as a reverse bias diode condition. That means, as we know, the current is tried to flow anode to cathode, as the junction J2 is reverse bias, that is why there is a question for formation of the depletion layer. Once the depletion layer has formed, then it blocks the current flowing as well as the total voltage is appearing across the two terminal anode to cathode. That means the device is under off state, yet we are using forward biased. That means we can say we can using the forward biasing condition at this particular condition, junction J2 is reverse biasing condition. That is why the depletion layer has formed, and due to this reason the device is not working or not in conducting state. Okay, suppose, so what happened in this particular case, just like a reverse bias diode, a small amount of current starts flowing across throughout the device, across junction J2 also, due to minority carrier movement. This is called reverse leakage current like a diode. Here we can say it is a forward leakage current due to presence of junction J2 as the depletion layer has formed. Right? Okay. One more thing. Suppose we are increasing the amount of voltage. What happened? Suppose at the first case we have implemented suppose 50 volt. Now we are increasing the biasing voltage suppose 50 volt to 100 volt. That means then the tendency of the leakage current should be increased. Suppose again we are increasing the voltage, suppose a huge value, suppose 400 volt. I don't know, that depends on the specification of the device. Suppose assume we have given suppose 400 volt. What happened? Then suppose it is a particular critical value of supply voltage or biasing voltage at which the junction J2 is permanently damaged or junction J2 is vanished due to avalanche breakdown of the majority carrier. Okay, that means what? If the junction J2 is vanished, that means there is a no question for any the blocking, means there is a no question for opposing the original anode current. That means that then the device starts conducting easily in this way, right? Then we can say the device is under on state. That means we can say if we are not applying any gate triggering pulse, suppose we are increasing the biasing voltage, anode is more positive with respect to cathode to a particular value, then the device starts conducting as the depletion layer of the junction that is destroyed. Okay. So that means we can easily understand in forward biasing condition J1 and J3 is in forward biasing condition, but the junction J2 is in reverse biasing condition. Okay. Right. Now think about the reverse biasing condition. Means suppose consider the cathode is more positive with respect to anode. Then current try to enter from cathode to anode. So in this particular case what happened? Then the junction J3 is reverse biasing condition as the current is try to flow from N layer to P layer, as well as junction J1 is again reverse biasing condition. Okay, but whereas the junction J2 is right now in forward biasing condition. That means in this particular case what happened? There is a tendency of the formation of depletion layer across junction J3 and junction J1. That means it will block the total amount of reverse biasing current. If we are increasing the huge amount of the reverse biasing voltage, then what happened? Then once the junction J1 and J3 can be permanently damaged and it will provide a huge amount of heat as the huge amount of loss behind the presence of two depletion layer across J1 and J3. That is why the device can be also permanently damaged. So this is not our required. That is why we are trying to operate this device only for forward biasing condition. So whatever I told, whatever I have discussed, this is due to not application of the gate. Okay, so this is the actual operation for Thyristor. Okay, that means in forward biasing condition, keep it in your mind, only the junction J2 is reverse biasing condition and depletion layer has formed. In reverse, when the device is under reverse biasing condition, only the junction J1 and J3 is, the both junctions are in reverse biasing condition and tendency to formation of the depletion layer across the both junctions J1 and J3. That is why always we are trying to operate this device only to the forward biasing condition, means anode will be more positive with respect to cathode. Okay, so this is all about for the operations of Thyristor and the basic construction and ratings. Keep it in your mind, the ratings of the power electronic switch like Thyristor, that is so much high, which can handle and which has the capacity to handle the power almost 30 megawatt and more than that somehow. Now, VI characteristics. See, is a very important part to relate the operation of SCR or Thyristor. So, before going into this topic, let me draw the schematic diagram through which we can plot the VI characteristics. So, consider the schematic diagram here. Is a variable resistance which is connected to the supply voltage, suppose E, and this is connected to the load, and load is connected to anode of the device, as we know the symbol of the Thyristor, and cathode is connected to the back to the supply, and gate is connected to another variable resistance to the different supply voltage. Okay, this is a schematic circuit diagram through which we can represent the VI characteristics, that is load. Okay, so this is a supply voltage which is normally used to biasing the device, and this is gate terminal. This is gate terminal which is connected to the separate voltage source here, and the switch is there. Suppose this stands for S, the switch is there. So initially, whenever we are going to define the VI characteristics of SCR, just the switch is open. Okay. So first we consider two axes like this one, that is voltage axis and this is suppose current axis. Fine. So I know the normal working principle. At the initial case, we have given the biasing with small amount. That is why, due to presence of the junction J2, small amount of leakage current starts flowing. Suppose we are increasing the biasing voltage, leakage current can be increased. After increment to a certain value, when the voltage reached a critical amount up to which the depletion layer of the junction J2 can be vanished, then the device is under on state. The similar thing, just we are going to plot in VI characteristics. Okay, that means initially we will start from 0. That means no voltage is there. Suppose we are increasing the voltage, then the device is still in blocking state up to this particular region. That means this is the very small amount of current that is called leakage current, and which is actually created due to the presence of the depletion layer across junction J2. But when it will reach a particular amount of voltage, suppose which is defined by VBO or breakover voltage, then junction J2 can be vanished due to avalanche breakdown of the majority carriers. Then what happened? Then the switch is in on state. Once the switch is in on state, that means what? That means the total voltage is not appearing across the cathode to anode, then the current is sharply increased. Okay? As it's known by everyone, when the switch is off, then the voltage is appearing across switch. When the switch remains on, then the no voltage is appearing across switch, then the current starts conducting. Similar thing can happen for this semiconductor switch. So up to the point of B, VBO, that means there is a no question for on state. That is why up to 0 to VBO voltage, it is called actually the blocking state or forward blocking mode. In this mode of operation, that is only the leakage current, this is the amount of leakage current, very small in magnitude, this is the amount of leakage current only is flowing throughout the switch. That is very negligible amount. After we are crossing the voltage, or we are trying to increase the voltage above VBO, then what happened? Then the switch is under on state. That means this is the voltage which was, the first case was blocked by the switch. Now the voltage is not appearing across switch for ideal case, but here very small amount of voltage drop can be appear for due to presence of the 4 layers and 3 junctions. Means that this amount of voltage is not appearing across the A to K. Then the device starts conducting and current will be gradually increasing just in this manner. Okay. That means what? Once the switch is on and switch is coming in on state and become on, then the voltage VBO, which was presently was 0 to VBO, now the voltage falls to very small in magnitude. Then suppose we are increasing the forward biasing voltage, as there is a no question for junction J2, no barrier of junction J2, then the current is increased rapidly with respect to small increment of biasing voltage. Okay, but here this slope, this is the slope which is defined by this one. This is called actually forward. This is happened for the forward conduction mode, and this is called actually forward voltage drop due to presence of 4 layers and 3 junctions. Okay, junction itself has some resistivity. As we know, every PN junction there has some resistivity. That means there must have some ohmic drop, due to presence of 3 junction as well as the 4 layers, this is the amount of voltage drop. That is why this is called on state voltage drop. Okay, that is why it will take this kind of shape from this one. Okay, so this is all about for off state to on state or blocking mode to on mode. Now think, suppose we are trying to switch off the switch. So how can it possible? Suppose we are trying to off this SCR. Then SCR becomes off when the anode current falls to below holding current, unless it never can be off, because off means that every junction should be recovered or there must have some blocking state that will be erased across the device. That is why the switch can be off only by reducing the anode current below at a particular current which is called holding current. So suppose we are trying to off the device. That means the anode current should be decreased. Again decreases. After certain time, see up to this point at which the devices were started conduction. But in this particular case still the device is not off, in off state. That means it can be off if again we are reducing the current to a particular value up to suppose this point, which is called actually IH. This is called holding current. That means when the device will fall, the anode current of the device will fall up to the holding current and below at this holding current, then the switch will be off state. That is why this is called holding current. And suppose when we have implemented the huge amount of biasing voltage and the device start conducting at a particular point, which is suppose defined by this current, which is by suppose IBO due to presence of voltage VO. This is the current. So suppose somehow for some experimental purpose that is easily identified that suppose at this particular case, if the thyristor can be on, but thyristor can be off also, means the firing angle, this firing purpose is uncertain. Means I want to share some word. Suppose when we apply the maximum biasing voltage or critical value, that is VBO, then obviously it will reach the same thing due to application of VBO, that is IBO. That means we can say IBO is a particular amount of current at which the device just starts conducting, right? But when suppose at this particular point, when the device just starts conducting, we are removing the voltage or we are decreasing the biasing voltage. Then the device can be in off state. That means the device not will reach the conduction state. That means we can consider another current, suppose this one, which is defined by IL, which is called latching current. That means suppose at this point of IBO, the device starts conducting initially, but still you are holding this amount of voltage VBO, then the current is rises, okay? And when the current will reach IL, then we are suppose removing gate or we are supposed decreasing the small amount of voltage, but the device still in under on state. That is why this is called latching current. So we can easily say latching current and what is holding current. So holding current means is a minimum amount of current which is associated for turn on process of thyristor and IL which is associated for maintain the conduction process of thyristor. Both are actually very small in magnitude, that is true, but keep it in your mind. That means IH is a minimum amount of current which is maintained to, which is able to maintain the on state of the voltage, of the switch, below which the switch must be in off state, and IL is a latching current which is the minimum amount of current which is normally maintained to conduction process of the SCR, below which the SCR can be on or can be off. That is the uncertainty. That is why this is to the fixed value IL and IH. Okay, fine. So from the above discussion, we can conclude all the cases we can conclude all the cases that is IL must be greater than IH. Okay, that means latching current is always greater than holding current, and in numerical value normally IL is equal to 2 to 3 times of IH. This is normally we can conclude from some experimental validity. Anyways, so now think about the reverse biasing. That means we are easily identify what is the breakover voltage, what is forward blocking state, and what is forward conduction state. Now see, if the cathode is more positive with respect to anode, so what happened? As we know, in reverse biasing condition, two junctions are responsible to form the depletion layer, that is junction J1 and J3. That is why in reverse biasing condition, again the reverse leakage current starts flowing. After certain time, it is rapidly increases with respect to the reverse biasing voltage. So this is actually called VBR or reverse breakover voltage. At this particular voltage is a critical amount of voltage in reverse direction. If under any circumstances, if we apply this amount of voltage, then it provides a huge amount of loss, it provides a huge amount of heat, and due to this amount of heat, the device can be permanently damaged. That is why to reach this amount of voltage, this is not our requirement. So all the cases we are trying to operate this switch in a particular mode, that is well defined. First one is called That means from VI characteristics we can say there is a three mode operation, that is first one reverse blocking mode. This is the reverse blocking mode, okay, up to 0 to 3 VBR. That is forward blocking mode. This is 0 to VBO and this is called forward conduction mode. So from VI characteristics we can say it has three mode of operation. Number one, that is forward blocking mode. This is forward conduction mode. The characteristics is and the last one is, that is reverse blocking mode. So in this way we can analysis all the VI characteristics and which has three blocking modes. Okay, thank you. My next session, that will be reflected on the lecture 2, in which we will discuss about the topic on Thyristor turn-on methods. Okay, thank you.